Okay, so I'm now going to bring you a classic model, and this is the Markowitz portfolio optimization. And the idea is that when you're putting together a stock portfolio, you want a balance between return and risk. And generally, higher stocks that give you higher return are more likely to have higher risk. So what we need to do is we need to kind of we can do it either way. We can minimize variance for a certain return, or we could kind of maximize return for a certain variance. In this case, we're expecting we want a return of 10%. And for that return of 10%, we want to actually minimize the variance. So let's just look what data we have in this model. So we have the expected return of 3 stocks. We also have the variance, the covariances. I think it's chapter 4 you need to go back to if you want to just remind yourselves of what variances and covariances are. But it's just literally the amount of variation in the stock. So a stock with high variance the return is going to fluctuate. You might have very high return one day and very low return the next day. Covariance looks at how two stocks kind of co-occur with each other. So if they both go up together and both go down together, then they have high covariance. If one goes up and the other goes down and they kind of have the opposite pattern, then they're going to have negative covariance. And what this matrix here gives is these diagonal entries, stock 1, stock 1, stock 2, stock 2, stock 3, stock 3, give the variance, and the off diagonal give the covariance. In this case, the covariance between stock 1 and stock 2, stock 1 and stock 3, and stock 2 and stock 3. As things are symmetric, we only need the upper triangle. For example, this value here is identical to this value. Now, I've taken the spreadsheet from the book and I've actually simplified it a little bit in that I've tried to put the variance terms we're calculating for the portfolio. I've tried to put them in exactly the same place as the variance covariance matrix. The book example kind of had them in 2 columns where the position really didn't match what was in the variance covariance matrix. So this should be easier to deal with. And so the idea here is we have the proportion of our allocation for 3 stocks, and that proportion needs to add up to 1. So let's just say we had 0.4 in stock 1, 0.4 in stock 2, and 0.2 in stock 3. Then we've got 100% of our allocation in the 3 stocks. And if you look at the model to the right, there's a constraint x1 plus x2 plus x3 equals 1, the proportion in each stock. We also have basically the return, and the return is basically just the weighted, and I'll just put that in myself, and I'll do this in a minute. The return is basically just the weighted sum of the expected returns. So this is just going to be some product of our proportions multiplied by the expected return. And in this case, for this portfolio, we get just over 10.2%, but which is our constraint. So that actually meets this constraint that our return is over 10%. Now the variance of the portfolio is basically these values multiplied by the amount we have in the stock, so weighted by the amount we have. Again, we're weighting, but this time as the covariance is for like 2 stocks, we need to weight by both stocks. So for these kind of values here, the diagonals, stock 1, stock 2, stock 3, it's basically we're summing up the proportion in the stock squared multiplied by the actual variance in the stock. So let's just take this term here. We have, so this is for each of the k variables. We have the variance with itself. So it's these 3 values here. basically these three values here. And for each of these K, this is just saying for each of the K stocks, for stocks from 1 to 3, we're calculating this value, stock 1, stock 2, and stock 3. And it's basically the variance times the proportion, the xi squared. So that's the contribution to the variance for stock 1. Again, with stock 2, times, and just note the squared has precedence over the multiplication, so it will do this to the power of 2 and then multiply by f7. If you wanted to be, 100% sure, you don't need to do this. You could just add brackets. And then finally, we do exactly the same for stock 3. Times. And now we can actually calculate the off variance. So if again you look at the right, to the right here, this is going to be 2 times the variance value, so the covariance. So for any between I and j, we take 2 times the covariance times the proportion xi and xj. Now the reason we do that is because, again, for this stock 1 and 2, we're not counting stock 1 and 2 in the other direction. So we actually are calculating this entry and kind of putting it here. So let's just kind of do that. So this is equals 2 times this covariance between stock 1 and stock 2 times the proportion for stock 1 times the proportion for stock 2. And now for stock 3, just make sure we have the right value. Yep, that's fine. And the reason it's double is we've multiplied by 2 here, and this is exactly half the variance of here. I just had the two entries, but in fact, that's correct. I was a bit worried that they were the same. Okay, so now let's go to stock 3. So again, this term to the right, so it's going to be 2 times the variance covariance times, this time it's going to be x1 times x3. Just check I've got all these right. So easy to make mistakes here. And this is both x1 and x3. And this one has x1 and x2. And the final one is x2 and x3. So it's equal to 2 times this value times the proportion in 2 times the proportion in 3. And the variance, let's just sum all of these up. It's a little bit wasteful because these cells have nothing in it, but it's actually easy. It's easier to do things in this triangle rather than in just a couple of columns like the book, because then you can match the covariance matrix. So we have our model. We're trying to basically minimize this variance value, where proportions have got to be equal to 1. Our kind of return, which is the weighted sum of our stock allocations and the expected return, has got to be greater than a certain value, and all the values need to be positive. So minimize variance by changing these cells subject to the constraints Okay, no, that's going to be the sum, sorry. The sum of all of these is going to be equal to 1. And then we've got the return needs to be greater or equal to the target return. And the variables are non-negative. Now let's click solve. Okay, and I got the same answer as the book, which is always a good thing. As I said, I'm going to keep the book one for you. The book is exactly the same, but it just, I said, put these covariances in columns, and I've just tried to match it to the actual terms. And that's the Markowitz variance kind of model. So, I mean, what we could do is we could play around a little bit. So the moment the variance is 0.012, imagine that we wanted, we obviously can't go more than 12%. But imagine if, because that would be impossible given the stocks we have, imagine we wanted 11% return. I could click a solver. And then we have to have much higher variance there. So let's just go back to 10%. And solve. And that's the Markowitz portfolio model. And as I said, I won't have a blank one here. You can remove and add things yourself. I just wanted to keep the book version as reference, as I did it a little bit, what I thought was a little bit simpler.